Let's use the either the root test or the ratio test to decide what inputs of x we can put in and get out a convergence series. Okay, so let's try the root test. So we are going to take a look at the limit as n goes to infinity of the nth root of the absolute value of a n. So this is going to be the limit as n goes to infinity of the absolute value of x plus 5 to the n that we're going to raise to the 1/n power. Okay, so this is the limit as n goes to infinity of the absolute value of x plus 5, because the nth power and the 1/nth power cancel each other out. Alright, so we end up with just a limit of absolute value of x plus 5. If the absolute value of x plus 5 is less than 1, then the series converges. If the absolute value of x plus 5 is greater than 1, then the series diverges. So let's find where these cutoff points are. Okay, so x plus 5, the absolute value of x plus 5 is less than 1, means that -1 is less than x plus 5 is less than 1. So x is less than -4 and more than -6. Okay, so it's inconclusive. It's too close to call. When x is equal to -4 and when x is equal to -6 using the root test. But otherwise, if x is between -4 and -6, we could say, yes, this series converges. And let's actually try plugging in those endpoints. So let's start by looking at x equals -6. If I plug in x equals -6, I get -6 plus 5 to the n. Whoops, and that's n equals 0 to infinity, -1 to the n. This one diverges. If we plug in x equals -4, then we see this is n equals 0 to infinity of -4 plus 5 to the n. And so this is the series adding up infinitely many copies of just 1. Okay, and this one diverges too. Both of them diverge by the divergence test, by that nth term test. Okay, so where does which x values do we have this series converging for? Well, if our values are between -6 and -4, then this series converges.